Good afternoon, YouTubers. Today we're going to be solving this differential equation that is shown here. This differential equation, you can get this one when you do a mass balance around a vessel or a tank like this one, that you have a flow in, that's called Q1, and a flow out called Q2. But Q2 by definition, if you use Bernoulli equation, you will end up with something similar to this, except that this has this friction factor here, which also is called the discharge factor. And in most cases, when you have sharp orifice like shown here, it's about 0.62. So we're gonna take that friction factor as 0.062 as shown here. The rest of the parameters that shown here, flow in, Q in, the area of the orifice, and the square root of 2 times the gravitational acceleration times h, the height of the tank in whatever point, with an initial condition that at time equals 0, h equal to some initial value. Now we also have here the area of the tank, which is also based on the diameter of the tank, so you can calculate area based on that, sort of like a circle here, and so here as well, where you have a diameter for the orifice that will eventually help you to calculate A0. So that's basically the differential equation, and here is a solution, analytical solution. When I take a look at this analytical solution, it's kind of cumbersome because it's t equal something in function of h. Would be better the other way around, but hard to get that out. So anyway, what we're going to do is solve this differential equation in Simulink, which is already ready here. So double click here somewhere, and let's bring the first thing that we're going to bring is an integrator block. Integrator, what is it? Right there. Bear with me. This Simulink, this version of Simulink, this 2023 version, slow. I don't know what's going on, but very slow. Now I got that. Now this is the story. We're gonna add here, let's bring a scope here as well, scope, and so we can monitor what we're doing. And let's bring that here. And now and let's tie these two together. And now whatever is coming from this block, from this integrator, is when you integrate this. So that would be h right there. Now this is the story. We need to feed back all these into this integrator so that it will do that. Now how to do that? Let's double click here, a function, a MATLAB function, so that we can grab everything here somehow. And let's see. One of these days it will pop. Maybe not today. Wow. Let me get out of here somehow. If I can touch it, it kind of got open as well. So there we go. Now we're gonna tie this guy is gonna be tied to this guy, but here's the story. This, whatever is coming through here, must be then the part that we're gonna be integrating. So that's gonna be dh over dt. And now what we need to do is put all these somehow here. So and I really like this one compared to let's see, compared to function, a simple function block like fc. Compared to this one, this only have one input, one output. Now we're gonna use this one and double click on it, and when you do that, then you see that you can change few things here and there. Now the axis is not going to be y anymore, it's going to be h prime for the In this case, we are changing this part here. And now it's going to be function of how many parameters do we want here. There's one called Q1, so definitely we want that Q1. And how about the others? We have A0, and we have AT, and also we have H. With those parameters, I think that we're gonna get this done. And now what's why it's not longer available? It's gonna be called, in this case, the exit of that block is we're gonna call it H prime. H prime equal, and here is what we're gonna do. We're gonna write all this the way it is here. So it's gonna be a parenthesis Q1 minus 0.62 times this parameter A0, sorry, that times A0 times parenthesis 2 times 981. Remember, we're gonna use centimeter and second here, so 2 times H, and that's a parenthesis there, another parenthesis there, and that will be elevated to 0.5 for the root. And now there's another parenthesis here, which is have to tie with this one, and all that divided by AT, the area of the tank. And I think I got everything. H prime Q1 minus 0.62 times the area of the orifice time 2 times G times H, all that to the square root of that, divided by 80 right here. So I think that we got everything. We go back, and now we got all the parameters that we need, and it looked good. Now here's the story. We need H from here, that will do. Now, how are we going to define A0 and AT? This is where this might come handy, because basically what I'm going to do is here. Now, I need a block. Well, I need a couple of blocks here. This constant block, actually. Constant. We're going to use that constant block. We're going to use 3 of them. One for Q1. I'm going to put it that there. That's for Q1. So basically, the idea here is that you have the flow into the vessel. So you put a number here. I don't know. Let's put a number there. About wow, it took a while to open. About 100 cc per second. That will do. Now I need another block of this. Copy, paste, make it faster. And I need another like this. Copy, paste. Get this a little bit. There we go. And these are to set the parameters here that are associated basically. There we go. And I need another of these. Copy, paste. And we got this straight. We got pretty much everything done, except that I have to change a few things here and there. Actually, this is not Q1 anymore, but that would be A0. Actually, that would be the diameter. That would be the diameter of the orifice, and actually this one definitely will be a 0. There we go. And And here you put the diameter of the orifice, and that diameter, I don't know, will be, what value should I put there? That should be about 1.5 centimeters. Apply. And so now here's where you're gonna calculate the area here inside here, this function. So for the area, remember this is a function of u1, and so this is what we're gonna do. We're gonna receive the diameter, and under u1, so this is gonna be pi 3.1416 times it's gonna be u1, put it this way, square, divide by 4, and we're gonna copy this because basically it's the same that I'm gonna do right here as well. And we're gonna change a few things here and there, and so that's okay, but here is not longer. Actually, start by here. That's the diameter of the vessel. Let's see, 50 centimeter, that will do. Apply, okay, and let's change this. That's diameter of the tank, and here what we're gonna have there is basically 80, what is coming there, and that's what we're gonna receive here, 80. And it looks like we got pretty much everything that we need. Like, for example, the diameter, the flow in, remember the unit, right? And all the math, it just happened here, which I can, H prime, I can copy everything if I want to. And Q1, looks like we got everything done. And let's fix this. Looks a little bit ugly. There we go. All right, good enough. Now let's check the initial condition. Here, there's an initial condition that at t equals 0, I have to have a certain height elevation in the vessel. So let's pop here. Right now it's at 0, so from 0 it will take some time to fill to certain height, and that's going to be a steady state value. Eventually it's going to hit. Now 10 seconds, let's put 100. Let's see where that will take me. And so let's run. That's gonna take a while. Backing up all unsafe model, and we'll see. This is real time, folks, so whatever happens will happen. Wow, definitely it's a lot slower. This new version of 2023 is definitely very, very slow. Whatever, at the installation time, I guess we have to do something. I have to reinstall this version somehow and get everything out, whatever I'm not using, because somehow it takes forever. It takes forever. Version 2019 was super fast compared to this one. I'm not against of improvement, but again, it's just mind-boggling. Let's see where we are now. It is execute. Let's double check here and let's see what we come out with. It's popping in another window, so I gotta move this window back here somewhere, right here. Now I can see that it's moving to a particular steady state. It's not going to be that high. This is centimeter. So to expedite these and to do kind of a faster curve, let me change a few parameters here and there. Let's make the vessel 50 is okay. 1.5. Let's increase the time here, and let's make this 500. And let's see how that will work. There we go. Getting to the 4 here pretty much at 500. That's a steady state value. You want a higher value instead of 4, then you have to increase this flow. Let's increase this to 150. Let's see how this looks like. So the flow in, this flow in is about 150 with the unit of centimeter cc, for example. Here I should say, just to so that you understand what I'm doing, cc per second. And let's run this again. There we go, a little bit higher. Yet this is way too big for this type of flow that I'm using here. I have to reduce this, like, let's say to 1.2, so the vessel gets somehow significant high here. 1.2, let's say okay, and let's run again. 16, getting better. 16 centimeters, and still way too big. Let's reduce that to 1 centimeter. Let's see what that will do. All right, now you see it's not getting yet to the steady state, but it's coming to a kind of significant high, about 20 centimeters here. So so I have to increase the time here so I can get that to a better steady state value and find out what it's gonna be. It's not yet at steady state. Well, about 1,000, and it's not getting there. It's not even close to 1,000. Now it's moving faster. When it loads everything, now it's moving quick. That's one of the things that is doing better now, that the simulation are running faster, and I can see that I'm getting to a steady state of 40. So that starts to look good. Let's see. In order to expedite this faster, maybe I have to reduce this a little bit. Instead of 50, let's say 40. And let's see how that will work. Yeah, now I'm pretty much at a steady state here, 40 something, 45 somewhere, getting there. So let me reduce this a little bit more, maybe no more than 30 centimeters. That would be like a 5-gallon bucket, basically. That's what I'm looking at. This is a, you know, with that diameter, it's the diameter typically of a 5-gallon bucket. And so if I run that, oh, definitely, it's right there. Got 40 something, 47, 48, and so anyway, you got the dynamic of this. Now that's steady state value. No matter if you are coming from 0, it will get there. Now if I'm coming from way above, like for example, instead of the initial condition being 0, you double click here and put now how about 100. If you're coming from above, oops, 200, 100. If you are coming from above, what's going to happen is that it's going to look like this. It's going to go from the 100 down, but that's going to be, that steady state value will stay. For example, let's run that, and you can see it hit from 100, it hit back again the 48, and but it's moving pretty good. So anyway, as you can see, the way I did this approach for the differential equation was to use the MATLAB function so that I can add everything that I see here as a potential parameter. Like Q1, this could be a potential parameter. A0, the diameter of the orifice, area of the tank, and area of the tank as shown here. So Now, it's a function of h, meaning that h is just what is coming from the integrator. That's h. It's kind of a feedback to the system so that it can be taken here into this trick, and eventually you get the values. And well, folks, that's basically it. There's nothing more into it. That's very straightforward. Again, the idea is to have parameters somewhere here that you can, access them quickly and know what you're doing. Well, folks, that's more than enough. And as always, have a great day, whatever be your final destination.